Consider this example. Let's say you work at an acute care facility for stroke survivors. And in the previous year, using the treatment that you've normally used, you recorded results at discharge for each client using the timed up and go test. And then this year, you introduce a new intervention, so something different. And you want to know if the results for clients on the timed up and go test was better for the clients from this year who got the new intervention or the clients from last year who got the old intervention. Now, the timed up and go test is measured in seconds, and lower scores are better. So your data is ratio, and let's say you check and make sure that it's normally distributed. So how do you find out whether this new intervention worked better than the old intervention? All right, so here's some sample data, and important point here, even though these are laid out in two columns, these are two separate groups of people. This is not two measurements from the same person. So here's my data from my comparison group. And here's my data for my intervention group. And these are independent samples, right? So this came from one group of participants. This came from a second. Then this website is going to give you two different results for t-test. One, assuming that the sample variances are equal, and one not making that assumption. This unequal sample variances, that's a more conservative assumption. So if you have that option, I would encourage you to use the unequal sample variances. So here's the difference in means. So you can see there was almost a 3-second difference between the two groups, and the one-tailed p-value is well below 0.05. So this was a statistically significant difference. In addition, you're also getting the confidence interval of the difference of means. And once again, we're going to go with the unequal sample variances. And here you can see that the difference stretches somewhere between 1.3 seconds and so that's 2.9 minus 1.6, and then 2.9 plus 1.6 would be 4.5. So 1.3 to 4.5. And what that tells us is that we're 95% sure that if we had an infinite number of participants, we would see a difference somewhere between 1.3 and 4.5. And our critical value, remember, is 0. And since 0 is not in the confidence interval, we can say that we're 95% sure that there is some difference between the two. And the p-value tells us that the average difference, there's a very small chance that we would have seen that if there wasn't a difference between these two groups. And all of this refers to statistical significance. Clinical significance is a different matter. Clinical significance is determined by, well, is a 3-second difference on the timed up and go test worth doing the new intervention for? So maybe this new intervention costs a lot more money and takes a lot more time and requires a lot more resources. So 3 seconds difference really isn't enough. In that case, this isn't a clinically significant result. But maybe the new intervention actually is faster and cheaper. In that case, a 3-second difference is clinically significant. So statistical significance we have that really clear, objective p less than 0.05 cutoff. Clinical significance is much more nuanced and situation dependent.